Why have one way of multiplying when you can have two? Thanks, linear algebra! Hey everyone, and welcome to How'd You Get That, where we solve all your math and physics problems. Today we are continuing with vectors, but this time we are looking at the bad cross product. Remember from last time when we used the dot product to multiply two vectors together to get a scalar? This time we're using cross product to multiply two vectors together to get, you guessed it, a vector. So how do you use this thing? Well, there are, as we've seen before, two equivalent and yet different ways of describing the cross product. One using magnitudes and angles, and the other using unit vectors. Let's start with magnitudes and angles. In this method, the cross product is defined in this way. Vector A crossed with vector B is equal to the magnitude of A times the magnitude of B times the sine of theta, which is the angle between them. So let's jump straight into this with an example. Let's say that A is equal to 5i hat plus 12j hat, and vector B is equal to 6i hat plus 8j hat. First, we'll find the magnitude of the two vectors. So the magnitude of vector A is equal to the square root of 5 squared plus 12 squared, which, doing a little math, we find is equal to 13. And the magnitude of vector B is equal to the square root of 6 squared plus 8 squared, which, doing a little math again, is equal to 10. Now, to find the angle between those two vectors, theta, we're going to have to take the difference between the angles that each vector makes with the positive x-axis. So let's take a look at that here. We can find each using a little bit of trigonometry. Basically, the tangent of each angle is equal to the y component of that vector over the x component of that vector. Taking the inverse tangent of all that, we find that ultimately the angle between the two vectors is equal to about 14.25 degrees. So taking all that information and plugging it into the cross product, we find that vector A crossed with vector B is equal to 13 times 10 times the sine of 14.25. All that is equal to 32. 14.25 is an approximate value for the angle between the two vectors, but 32 is actually an exact answer here. We're going to see that it actually is an exact answer using the other method, but suffice it to say, when I use 14.25, I get an answer close enough to 32 to verify that the answer actually is 32 if I'd used an exact angle. Now this method gives us the magnitude of the cross product. It unfortunately does not give us the direction of that vector. In order to find the direction of the vector, we're going to use something called the right-hand rule, which often you don't learn until electricity and magnetism. But now we're going to learn it here. So the first thing you're going to do is point your fingers in the direction of the first vector. And then you're going to sweep your fingers in the direction of the second vector through that angle. And your thumb points in the direction of the cross product vector, which in this case is into the page. Now, be careful when you do this. One, you don't want to use your left hand, and two, you can't sweep through your wrist. So if the second vector is over here, I'm going to have to flip my wrist around and sweep through to the second vector. Okay, so now the cross product of A cross B is equal to 32 in the negative z direction into the page. But now let's take a look at the unit vector method. Now this requires some matrix algebra, which if you haven't been introduced to it, can get a little complicated. I know my education in matrices was scattered at best, so unless you've taken linear algebra, you may not have seen this before. But all we need to solve for the cross product, at least in physics, is something called the determinant of the matrix. In a 2x2 matrix, the determinant of that matrix is found just by subtracting the cross product of the elements within the matrix. We're going to do something similar with our cross product here. So A cross B is equal to the determinant of this matrix. First row, I hat, J hat, K hat. Second row, AX, AY, AZ. Third row, BX, BY, BZ. As you can see, our first row is just unit vectors. That's going to always be what it is when we're taking the cross product. The third column here is the z direction, which in our example is just going to be 0. But it is important that we include it. So in order to find the determinant of this matrix, we do a similar thing that we do with a 2x2 matrix by taking the difference of the cross products. But in this case, we're going to take a little bit more complicated strategy. So the first thing we want to do is build our matrix. So our new matrix is I hat, J hat, K hat, 5, 12, 0, 6, 8, 0. First thing we're going to do is draw a line through the first column and save the first element of the first column, I hat, off to the side. We're now going to take the difference of the cross products of the remaining elements below the first row. So in this case, that would be 12 times 0 minus 0 times 8. We're going to take that difference, which is just 0, and multiply it by I hat, which is equal to 0 I hat. We're then going to move on to the second term of our determinant. We're going to cross out the second column now. That has j hat at the top, and we're going to save j hat off to the side. We're now going to take the difference of the cross product of the remaining elements below the first row, which in this case would be 5 times 0 minus 0 times 6. We're going to take that difference, which is just equal to 0, and multiply it by negative j hat this time. And finally, we're going to find the last term in our determinant. First, we're going to cross out our first column, which has k hat in it, and save k hat off to the side. We're then going to take the difference of the cross product of the remaining elements below the first row, which in this case would be 5 times 8 minus 12 times 6. 5 times 8 is 40, 12 times 6 is 72. That difference is just negative 32, and we're going to multiply that number by k hat. So our determinant is equal to 0 I hat minus 0 j hat plus negative 32 k hat. Simplifying down, we find that A cross B is just equal to negative 32 k hat. And as you can see, the magnitude of this cross product vector is 32. And we're also told explicitly what the direction of that vector is. It's in the negative k hat direction, the negative z direction, or into the page, just like we found before. Now you can see that using unit vectors is a whole lot more involved than using magnitudes and angles, but sometimes it's the only way that we can find the cross product of a vector, especially if we want to find something more complicated, like say the equivalent expression for the triple product, A cross B cross C, it's equal to back cab. But using unit vectors also gives us that explicit notation for what direction the cross product vector is pointing in, without having to resort to the right-hand rule. So 2 quick things to know about the cross product. The cross product is not commutative. A cross B is not equal to B cross A. Order is important. Also, looking at our magnitude angle notation for the cross product, we can see that if theta is equal to 0, the sine of theta is equal to 0, and therefore the cross product will go to 0. So if I have 2 parallel vectors, their cross product will be exactly 0. So there you have it, the cross product. Useful for these wonderful properties: torque, the Lorentz force, angular momentum, the force on a current carrying wire due to a magnetic field, Stokes theorem, curl, and many more. Thanks so much for watching. If you have any questions, leave them in the comments below. And if you have any suggestions on what you'd like to see in a future episode, leave them there too. Hit that like button, subscribe for more math and physics content, hit that notification bell, and I'll see you in the next problem.